Okay, as we continue, we also have the variation of the I sub f with df all over d and u sub s, which is given in table 11.3. And we have to take note that when df is equal to 0, the value for I sub f is equal to 1 in all cases. So we have here table 11.3. We have the variation of I sub f. We have to take note of dl over d and df all over d so that we can have the value for I sub f. So for elastic settlement of a rigid foundation, it can be estimated as, for rigid foundation, the elastic settlement is approximately 0.935 of the elastic settlement for a flexible foundation. Due to the non-homogeneous nature of soil deposits, the magnitude of E sub s may vary with depth. For that reason, Boltz recommended using a weighted average value of E sub s. And E sub s is given by this equation, wherein our E sub si is the soil modulus of elasticity within a depth of delta c, and z bar is equal to h all or 5d, whichever is smaller. So representative values of the modulus of elasticity and Poisson's ratio for different types of soil are given in 11.4 and 11.5. So we have here the representative values for the ES, modulus of elasticity of the soil, and for the Poisson's ratio, which is dependent on the soil type. So we have here a sample problem. A rigid shallow foundation which has 1 meter by 1 meter in plan is shown in 11.4. Calculate the elastic settlement of the center of the foundation. So we have to take note that we are given with the width of the foundation and the length of the foundation, which has 1 meter and 1 meter respectively. So our z bar is 5 meters, which is equal to 5 feet. So we have here from this is our figure for our problem. So we have the depthness of our df, which has 1 meter. The foundation is 1 by 1 in meters, and so we are going to compute for the settlement of the center of the foundation. So we're going to have the value for E sub s, the modulus of elasticity of the soil given by this equation. So you simply have to substitute, which is summation of this ES, which is from this one, which is 8,000 times 2, then plus 6,000 times 1, plus 10,000 times 2. So that is all over z bar, which is this is the depthness of this, which is equal to 5, and that gives us 8,400 kilonewton per meter squared. And for the center of the foundation, our alpha is 4, so we have to identify our m prime and n prime. So that is L over D, which has 1 over 1, which has 1. N prime is equal to H all over D all over 2, which gives us 10. So from table 11.1 and 11.2, our f sub 1 is equal to 0.498 and f sub 2 is equal to 0.016. So we have to make use of table 11.1 and 11.2. Our m is 1, our n is 10. So it simply gives us the value of 0.498 for f sub 1. The f sub 2 using 11.2, n prime is 10, our m prime is 1, so it gives us 0.016. So we have now the value for f1 and f2. We can compute for the shape factor, substitute the value here. We're given with our u sub s, so which is 0.3, and shape factor now is 0.507. So for, again, df all over d, which is equal to 1, and L all over D is equal to 1, so our mu sub s is equal to 0.3. So from table 11.3, our I sub f is equal to 0.65. So from our table 11.3, from this table, L over base 1, Vf is equal to 1 mu sub 3 is equal to mu sub S is equal to 0.3, so our I sub F is equal to 0.65. So we have now the value for our mu sub, I sub F. So we can substitute for our equation for this flexible equation settlement. The settlement for flexible foundation is equal to 14.3 millimeters. So we can compute now for the settlement for a rigid foundation, which is just multiply approximately to the 0.93 times 14.3, it gives us 13.3 mm. Now we move on to normally consolidated and overconsolidated plates. So for the figure shows that the upper part of the E-log sigma prime plot is somewhat curved with a flat slope, followed by a linear relationship for the void ratio with log sigma subprime having a steeper slope. This phenomenon can be explained in the following manner. So for this one, we have the plot of E against log of sigma subprime showing loading, unloading, and reloading branches. And we have now the graphic procedure for the determining pre-consolidation pressure. So these are the illustration for the linear relationship for the void ratio with log of the effective pressure. So a soil in the field at some depth has been subjected to a certain maximum effective pass pressure in its geologic history. This maximum effective pass pressure may be equal to or less than the existing effective overburden pressure at the time of sampling. The reduction of the effective pressure in the field may be caused by natural geologic process or human processes. So during the soil sampling, the existing effective overburden pressure is also released, which results in some expansion. When this specimen is subjected to a non-consolidation test, a small amount of compression will occur with the effective pressure applied is less than the maximum effective overburden pressure in the field to which the soil has been subjected in the past. So the relationship can be verified in the laboratory by loading the specimen to exceed the maximum effective overburden pressure and then unloading and reloading again. So the plot that was presented a while ago for such cases in which CD represents loading, represents unloading, and DFG represents the reloading process. So we have here the figure illustrates its lead us to the two basic definitions of clay based on stress history. So we have the normally consolidated and the over-consolidated. When we talk about normally consolidated, the present effective overburden pressure is the maximum pressure that the soil was subjected to in the past. And when you talk of over-consolidated pressure, whose present effective overburden pressure is less than the which the soil experienced in the past. So meaning to say the maximum effective past pressure is called the pre-consolidation pressure. So the soil that was subjected to a certain pressure in the past, which is in maximum, that is what we call pre-consolidation pressure. So when we talk about normally consolidated, the present effective overburden pressure is maximum compared to the past overburden pressure that the soil experienced. When we talk about over-consolidated, meaning to say that the present effective overburden pressure is less than compared to the past effective overburden pressure. Ito's Casagrande suggested a simple graphic construction to determine the pre-consolidation pressure, sigma sub C, from a laboratory E-log sigma prime plot. So we have here the procedure. The visual observation, establish A, in which plot has a minimum radius of curvature. We're going to draw the horizontal line AB, draw the line AC tangent at A, draw the line AB, project the straight line portion GH of the E-log sigma prime plot back to intersect line AB at F. So the abscissa of point F is the pre-consolidation pressure sigma sub C. So This was illustrated on figure 11.13. So this was the suggestion of Casagrande. So the overconsolidation ratio, OCR, for a soil can now be defined as sigma sub C over sigma, which is sigma sub C prime is the pre-consolidation pressure of the specimen, and sigma prime is the present effective vertical pressure. So pre-consolidation pressure of the specimen, that was the maximum effective overburden pressure in the soil experience. Sigma prime is the present effective vertical pressure. In the literature, some empirical relationships are available to predict the pre-consolidation pressure. Some examples are given with this relationship. According to Polhari and Stas, sigma sub C prime over P sub A is equal to this variable, wherein P sub A is the small atmospheric pressure and Li is our liquidity index. According to Hans Bock, he has this relationship wherein we have the empirical coefficient alpha, which is equal to this expression. C sub U is undrained shear strength obtained from the shear test. Now we move on to pre-consolidation settlement. So let us consider saturated clay of thickness H, and it has a cross-section A under an existing average effective overburden pressure sigma sub O. Because of an increase of effective pressure delta sigma prime, the primary settlement S of C, thus the change in volume, can be given by this equation. So basically the change in volume is equal to V sub O minus V sub I, which represents the initial and final volume respectively. And this can be also expressed in this form, or the change in volume is equal to S sub S, which is the primary settlement multiplied to A. However, the change in the volume is equal to the change in the volume of voids. Hence, the change in volume can be given through this expression, wherein our V sub O and V sub 1 are the initial and final void volumes respectively. So we have here the illustration for a settlement caused by one-dimensional consolidation. So for this one, we have a soil, and you apply a consolidation process. So there is a change in volume on the original soil. So this is now the illustration for the change in volume for the original soil after a consolidation process. So we have here our change in volume, and of course we have illustrated our S sub C, which is our primary settlement. So our delta E is the change of void ratio, and of course change of V sub V is equal to the change of E delta E times V sub S, and our V sub S is equal to this expression, and E sub O, take note that that is the initial void ratio at volume V sub O. And of course, from our previous illustration, delta P is equal to this equation, and from this we can obtain the value for the primary settlement S sub C, which is now equal to H times delta E all over 1 plus V sub O. Delta is the change in void ratio, E sub O is the initial void ratio. Of course, our H is the height of our soil sample. So that is now the computation for the primary settlement. So